Welcome to The Explainer. Today, we're stepping right into the lecture hall for a comprehensive masterclass based entirely on the brilliant research and presentations of Dr. Nima Mahadian. We're going to be looking at the absolute bleeding edge of process control, unpacking the exact mathematical architecture that keeps massive, complex industrial systems from just spiraling into chaos. And here is our mission for today. We are going to process every single slide sequentially, right straight through. So grab a seat and let's dive in. Right out of the gate, here is our high-stakes premise straight from the source material. Standard PID controllers fail when systems exhibit large dead times. Just imagine building a multi-million-dollar industrial facility, relying on completely conventional, universally trusted engineering solutions, only to find out they're suddenly rendered totally useless by a hidden lag in the system. It's a massive problem. To understand why this happens, we really need to define the enemy here: dead time. It's the physical or computational lag between issuing a command and actually observing its effect on a system. Think of it like trying to steer a fast-moving car on a super winding road, but you're looking through a video feed that's delayed by, say, 5 seconds. You turn the wheel, nothing happens. You panic and turn it even more, and suddenly, bam, you've steered right off the cliff. That is the devastating physical reality of dead time. So here is our roadmap for today's lecture. First, we'll start with the dead time problem. Then we'll look at the math behind the delay penalty, explore the incredibly brilliant Smith Predictor solution, tackle the messy industrial implementation realities, and finally, face the ultimate complication, the MIMO paradigm. All right, part 1, the dead time problem. Let's officially begin our rigorous slide-by-slide analysis of this system architecture. Slide 1, Dr. Mahadian introduces the time delay compensator, also known as the Smith Predictor, with a stark reality check. As we read in the title, standard PID controllers fail when systems exhibit large dead times. Basic, everyday math just won't save us here. Advanced structural compensation is absolutely mandatory to keep these systems online. Slide 2. Before we introduce dead time, let's establish our baseline by looking at the anatomy of a standard feedback system. Let's trace every signal here. We start on the far left with our target set point. That feeds directly into the controller, which computes the required action. That command then passes to the final control element. Think of a physical valve. Along the way, outside disturbances might enter the physical process, which then produces our final output. And finally, that output is measured at the bottom and looped right back to the start to close the whole thing. This is the perfect, uncorrupted system before delay ruins everything. Slide 3. But here is the physical reality, and it's grim. Look at the 3 stark warnings mapped out here. Warning 1, sensor delay. Disturbances reach the comparator late. The controller just sits there, taking 0 action during this interval, and eventually acts on completely outdated information. Warning 2, forward path delay. The control commands execute late. By the time they actually reach the physical process, the system conditions may have already wildly changed. And the third warning? That's the deadly cycle. A disturbance enters, it's revealed late, a command is issued based on old data, and then the execution of that command is delayed. It is literally a recipe for total system collapse. Part 2, the delay penalty. Now that we've agitated the problem, let's pivot to the harsh mathematical and engineering consequences of this delay. Slide 4. Let's break down the exact mathematical anatomy of this open-loop equation shown right here. The top term represents our variable controller gain, while the bottom term represents our first-order process dynamics. The big question we're setting up for example 6-1 is this. If we subject this exact process to varying degrees of time delay, how exactly does it impact our ultimate gain and frequency? Slide 5. The answers are mapped right here in this Bode plot, visualizing our frequency response degradation. Just look at that visual drop in the amplitude ratio curve as the delay increases. It falls off a cliff. And the table on the right lays out the exact brutal numbers. When the time delay is a tiny 0.01, our ultimate gain is a robust 80.1. But increase the delay to 0.1, and that gain plummets to 8.56. Push the delay to a full 1.0, and our ultimate allowable gain crashes all the way down to just 1.52. Also, notice the phase chart at the bottom. The phase angle degrades massively as delay increases, basically plunging the entire system straight toward instability. Slide 6. This brings us to the real engineering consequence of process delay. The graphic here heavily contrasts our limits, having a dial cranked all the way up to a high gain versus being choked down to near 0. Applying a massive gain to a system with high delay results in catastrophic instability. Why? Well, the 3 engineering rules on the right spell it out perfectly. Rule 1. As time delay increases, the crossover frequency strictly decreases. Rule 2. The allowable maximum system gain absolutely plummets. Rule 3, which is our inescapable conclusion, we are forced to severely detune the controller just to maintain stability, which means completely sacrificing our performance. We simply cannot accept this. We have to find a structural compensation method.
Part 3. The Smith Predictor solution. This is where we introduce an incredibly elegant mathematical sleight of hand designed to completely eliminate that delay penalty.
Slide 7. First, we need to define the ideal open-loop response. Look at the block diagram. The process now explicitly includes our main villain, the delay block. The dark box shows the real equation, which contains the delay term and forces the system to use unsuitable old data. Now look down at the green box. This is our target. It's the ideal response equation. It has the exact same process dynamics, but it is perfectly stripped of that time delay factor. So, how do we actually get from the real world to the ideal world? We mathematically derive a predictive compensation signal. Step 1 is the premise. We mathematically add an artificial signal to the delayed output to create our ideal state. Step 2 simply substitutes our transfer functions into the equation. And step 3, that's the breakthrough. We isolate this artificial signal, creating a brilliant formula exactly as shown on screen that represents the exact mathematical differential between the current state and the delayed process state. Slide 9. Now we take that math and build it architecturally. This is the completed Smith Predictor architecture block diagram. Notice how we take a feed exactly after our controller and we route it down through our newly derived compensation block. This generates our predictive signal, which we then feed right back into an inner loop, adding it to our delayed physical output. Slide 10. Let's strictly explain the 3 dynamic phases at play here to understand exactly how this model-based prediction perfectly cancels out dead time. Phase 1 is the command. The controller outputs a control signal acting entirely on the assumption of 0 delay. Phase 2 is the prediction. An internal model runs in parallel, simulating that exact dead time differential to create a compensation signal. And finally, Phase 3 is the cancellation. By adding the actual delayed output to our internal prediction, the physical delay is mathematically removed from the feedback path entirely before it ever reaches the main comparator. It is absolute genius. Slide 11. But we have to pause and clarify a core engineering truth here. Conceptual representation versus physical reality. Look at the top diagram. Conceptually, it's like we are just tapping the line before the delay block to get our ideal signal. It's mathematically equivalent, but physically impossible. As the callout box clearly says, we cannot physically intercept a fluid, a temperature, or a pressure signal before its inherent transport delay actually occurs. You can't fast-forward physics. So the bottom diagram shows the physical reality. Since we can't intercept the transport fluids early, we must construct a parallel mathematical reality inside the controller's software to simulate that uninterceptable conceptual signal. Part 4. Industrial Implementation Realities. Now we need to complicate our perfect mathematical narrative by addressing the messy, highly imperfect realities of industrial application. Slide 12. Let's look at the delay estimation matrix. The stark truth written at the top is that the internal mathematical model will never, ever be a 100% perfect description of the physical process. So what happens when we guess the delay wrong? Look at scenario A, overestimating dead time, meaning the actual delay is less than our model. Look at those wild, spiky oscillations. This is fatal dynamic instability. The controller is acting on false future assumptions, causing severe execution errors. Now contrast that severely with scenario B, underestimating dead time. The actual delay is greater than our model. It forms a smooth, stable curve. It's safe. The system remains perfectly stable, even though the compensation is technically incomplete. The industrial rule of thumb here, always approximate your industrial delays downward. Part 5, the MIMO paradigm. We are pivoting to the final, massive challenge of this lecture, moving from these isolated single loops into heavily intertwined industrial matrices. Slide 13, this diagram vividly contrasts what we've learned so far against where we're going next. On the left, you see CISO, single input, single output. It's an exquisitely simple single pipe and valve. The only goal was just maintaining one variable near its set point. But on the right, that's MIMO. Multiple input, multiple output. Look at that spaghetti-like complexity of intertwined pipes, tanks, valves, and gauges. This introduces the harsh reality of controlling highly complex industrial systems where multiple variables have to be maintained simultaneously at completely independent set points.
Slide 14. Let's trace the anatomy of a MIMO process block. We have a set of control variables, our U variables, acting as inputs on the left, feeding into the process under control, which then produces a set of measured outputs, our Y variables, on the right. And you really need to emphasize the critical note, highlighted in orange at the bottom here. The number of system inputs and the number of system outputs do not necessarily have to be equal. You could have 5 levers controlling 3 outputs, or vice versa. It's rarely a 1-to-1 ratio. Slide 15. Finally, we break down the immense design challenges of these multivariable systems. Look at this heavily interconnected web of U and Y variables and question marks. The inputs on the left need to control the outputs on the right. The absolute simplest approach is just building multiple individual single loops. But as the slide clearly notes, this creates 2 massive design challenges. Challenge 1 is loop pairing. Should input 1 control output 1, or should it control output 3? Selecting the appropriate pair is the absolute foundation of MIMO design. Challenge 2 is coupling, or interaction. A change in one loop inherently disturbs the other loops. If one input changes an output, it might accidentally spike another completely unrelated output as well. Managing this cross-interaction requires highly specialized decoupling techniques. And that brings us to the end of Dr. Mahadian's framework, leaving us with a final, very provocative question to ponder. Can mathematical models ever truly tame the unpredictable chaos of complex industrial interactions? As we scale from single-delete pipes to massive interconnected facilities, the math gets significantly harder. But as we saw with the Smith Predictor, human ingenuity scales right along with it. Now, before we wrap, as promised, let's run through our strict verification checklist to confirm all source slides were successfully processed without omission. Slide 1, check. Slide 2, check. Slide 3, check. Slide 4, check. Slide 5, check. Slide 6, check. Slide 7, check. Slide 8, check. Slide 9, check. Slide 10, check. Slide 11, check. Slide 12, check. Slide 13, check. Slide 14, check. And slide 15, check. Total slides in the PDF, 15. Total slides explained, 15. Skip slides, 0. Thank you for joining me in the lecture hall today for this explainer. Until next time, keep analyzing, keep modeling, and keep learning.